Hello and welcome to this video. Here we'll be discussing how to model real-life scenarios with the straight line equations. The equation of straight lines, rather. Okay, so let's read this first example. We've been told that the extension of a spring with the mass of m attached to it is plotted on this graph here. So we've been told to calculate the gradient k of this line. So it doesn't matter which coordinate you take. If you've been given a graph, you can take any coordinate you like. If I take this coordinate here, is y value is 15, is x value is 300. So we have 300 comma 15. That's in this coordinate here. And we know it's going through the origin. So the origin coordinate 0, 0. Taking the equation of gradient, we're going to say 15 minus 0 divided by 300 minus 0. So simplifying that, dividing by 5 will give us a 3 over 60, and we can divide by 3 and we get 1 over 20. So either way, you end up with, no matter which coordinate you take, you can test another point there if you wish. You can take this coordinate, just take a coordinate where x and y are integers. So it will give you the same answer. K, rather, I should have used the same letter that the question gives us. K is 1 over 20. So then the next part of the question says, write the equation linking e to m. So looking at e's our y value. In these questions, y and x are replaced with other values. So y is e, so I write e equals to the gradient multiplied by value of x is rather m. So, and we have 0 intercept. Okay, so I just don't need to write plus 0. That's the equation connecting e to m. Then question C is saying explain why the value of k represents what the value of k represents in this context. So you check out the context of a problem is extension in meters per unit is here gram. So E the gradient is saying that the the extension will be 1/20th of every gram you add to it by, so the measurement of extension is centimeter. All right, so I'll show you what you should write here for part C here. You're saying the each unit of extension is 1 centimeter. So you will have 1/20th centimeter for every 1 gram increase. So make sure you write increase with increase because the gradient is a positive. Yeah. All right. M is a positive 1 over 20. So you say, therefore, K indicates that the extension of the spring increases by 1/20th centimeter, all right, for every 1 gram increase in mass. All right, so that's that example done. The next example here is saying a container was filled with water and the hole is made at the bottom of the container, so the depth of water is decreasing. So the table shows the values of depth of water and time. When you question one, part A is saying determine whether there is a linear model is appropriate for by drawing a graph. So you've been in the exam, you will be given a paper with x and y axes already on it. You have to plot them, those points. At time 0, you have an intercept of 19.5. You're putting those values, you're plotting them, and you join them with a straight line. What you notice, you try to connect them with a straight line. They may not necessarily be on a straight line. But in this case, because the straight line goes through all points, the answer to part A is that yes, a linear model is appropriate for this context because all the points form a straight line, or at least they're very close. If you had, for example, uh, some differences and the points didn't lie exactly on a straight line, you try to draw the straight line that is closest to all of these points, and you say, okay, if the difference is minute, if there's small differences, it's still a linear um, or rather linear equation may be applicable, and but you would have to test it. All right. So part B is saying deduce the equation of the line forming. So you figure out the equation of the straight line. You already know from this coordinate what the y-intercept is. So this value of 19.1 is your y-intercept, is the value of this b here. So all you have to do is take any other coordinate and figure out the gradient of this line. So we're gonna take two coordinates. Let's just take those two, subtract the y values. In this case, 17.8 minus 19.1, and the difference in x's is 10. I'm calling them x and y's, but it's depth and height. So that's the gradient. Finally, you put them together into one equation. You write it as d equals to negative 0.13t plus 19.1. That's the part B done. So part C is saying interpret the meaning of the coefficients a and b. Well, coefficient is a, and b, I would say b is intercept, right? So a is saying that for each unit of time, t is measured in seconds. So every second, the depth of water is falling by 0.13 centimeters. All right. So you say this, write them as value of the the gradient is indicating the depth of water changes by 0.13 centimeter, because that's the units. Make sure you use the units given to you in the context of the problem, and it's the gradient is negative, so therefore it's decreasing. Okay, and at the time zero, that's the initial depth of the water, 19.1 centimeter in the tank. Make sure you use the context of the problem to answer such questions. So part D of the problem is asking us to use the model to estimate when the container will be empty. Alright, so if you extend the graph here, at some point this uh, hit the time axis. Alright, so what is the value of depth of water is 0 here, isn't it? So we're looking for this time where when depth of water is 0, it's empty, isn't it? The word empty means the depth will be 0 or close to 0. So you set the depth to be 0, and you into this equation that we already figured out in part B, and you solve that. So when you solve it for t, you figure out that t is a positive 146.9. You put seconds in front of it because it's measured in seconds. Alright, so let's look at the third example here. This third example is saying, in time at year 1991, there were 18,500 people living in certain city. Planners of a project say the number of people increased by 350 per year. So write down a linear model for the population. Let's call this population P. We just abbreviating population to P of that city, Bradley Stoke. And we're gonna use letter T for years after 1991. So don't get confused with 1991. That's when time is 0. All right. So they were. So this is our y-intercept, P, or rather P-intercept. okay? Because at time zero, we saying that this is when time is zero. Don't get confused with the number 1991. That's we starting our model there, and every year the 350 people. So you write p equals to 18,500 for the intercept and increase. So the word increase is saying that the gradient is positive 350 t. T stands for year. Okay, so after year one, one will be multiplied by this. After in year two, two will be multiplied, and so on. So that's how I would have written the equation. So part B of the question is saying write down one reason why this model may not be realistic. Well, increase uh, because there are resources and there that people have to overcome. Population usually increases fast when there is a small population and grows exponentially. More people usually lead to higher growth. So, what you should say is that population doesn't in a linear rate at a linear rate. Okay, usually uh, it will grow in exponential fashion, which is non-linear. We'll look into exponential models by the end of the year, or rather in chapter 14. So good luck practicing and good practice done, and I'll see you in the next chapter.